we're going to look at a couple things here. I wanted to take this opportunity to sort of look at what is the right way to write equations, particularly exponential functions, because that tends to be a place where kids get a little bit thrown off or don't remember exactly how to do it. So we're going to look at that today. So we're going to look at taking a context and turning it into a function, okay? Here's this particular scenario. I made this town up. Can you tell? The population of Talmac was 150,000 in 1990, okay? The population grows by 5% every year, okay? Create a function that models the population, P, in terms of time in years, T, since 1990. So this is key here because we're just saying how many years have passed instead of being like, what is it in 1999 and having to put 1999 in the equation. This is already assuming that you're calculating how long it's been since 1990. So in like 0 years, if T is 0, then our population is 150, okay? And so this is what I call the repeated reasoning table. I picked it up from a friend, and it is an excellent way of thinking about how to build a function, okay? So a population is growing by 5% every year. So here's our original population, okay? And we're going to take 5% of that population, and we're gonna add it to the end, okay? So we now have 105% of our original population every year, okay? This as a number, just as a decimal, is going to be 1.05. So we'll practice this in class, which is figuring out what this multiplier is going to be when we do this. But after 1 year, our population, 150,000, if you take that 150,000 and multiply it by 100% and 5%, right? So 105%. We're going to get some number over here. In this case, the number is going to be 150,000 times 1.05 is 157,500. Now, I don't really care about what this answer is because I'm not going to be using this answer to build this next row here. Instead, I'm going to say that this chunk right here, we're going to take 5% of this new chunk, okay, and add it on. So what we had last year was 150,000 that we multiplied by this, right? So you're going to see this carry down. So this right here is equivalent to the value after 1 year, okay? And so after the second year, we take this amount and we get 105% of last year. Okay, we're going to get a new number here. Now, I don't actually care about what this number is because that's not the purpose of this activity. So the following year, we're going to get 150,000 times 1.05 times 1.05 times another 1.05, right? And so we're trying to start looking for patterns here. Okay, so, all right, we have 150,000. And here's last year, 1.05, 1.05, 1.05. There was last year, and here's this year, okay? So at some point, this is starting to get pretty tedious, right? Do you notice any patterns? You might look for things like relationships between the input and repeated reasoning. So in this case right here, there is one 1.05. And then here there are two 1.05s. And then there are three 1.05s. And there are four 1.05s. So we could predict that 5 is going to be 150,000 times 1.05 to the fifth, right? as in multiplying by itself 5 times. We could have also written this one right here as 150,000 times 1.05 to the fourth, but we didn't, but we could, okay? So once we've noticed this pattern, we can say that at any point in time, we're going to have 150,000, and the number of 1.05s that multiply our 150,000 is equal to the number of years that it's been. So we're going to say that this number and this number are always going to match. And so this is our rule. So if it says create a function that models the population P in terms of years T since 1990, our rule would be that our population in terms of time is equal to 150,000 times, this should be T, right? Because T is years, T, times 1.05 to T, which is the number of years since 1990. Okay, so that would be that rule. The next one, you guys, is a similar question, but in this case, we're losing value, right? So if we had our population, in this case it's a value, and we're going to lose 3% of it. So this 3% right here is going away. That's 3%, and he's going away. So the question is, what remains, right? And what remains if we lose 3% is 97%. So if this was $100 or $200 or $300, what would remain is 97% of that value, okay? So we're going to do this repeated reasoning again here. Okay, so at 0 years, we just say 24,000 was how much it cost. After 1 year, our 24,000 is only going to keep 97% of its value from the year before, which is going to be some number. And again, that's not the purpose of this activity. You can calculate that if you want to. 2, after 2 years, we had 24,000 and it kept 97% of its value. That was year 1. This is year 1 here. And then we're going to take 97% of that, right? Now this is kind of starting to look like what it did above. 3, 24,000, and then year 2's value was this. That was year 2's value. And then at year 3, it lost 3 more percent, so it's only keeping 97%. So we're starting to see that same pattern, right? Where you have 24,000 times 0.97 to the T, right? To the third in this case. Now we could continue on if we wanted to. Down, down, down. We're going to go ahead and say T here. So T. So after T years, we'll have 24,000, and just like before, when it was 3, there were 3 97s. When it was 2, there were 2 97s. When it was 1, there was 1 97, right? So we're going to say 0.97, and the number of those is going to be equal to the number of years. So here it was 0.97 to the third. Here it would be 0.97 to the second, right? And even here, you could even put it in it if you wanted to as to the 0, because those two things would say 0.97, anything really, to the 0 is just 1, and so 24,000 times 1, right? 100%. So you wouldn't even need this if you didn't want to. So to the T, and that is our value of our car in terms of the number of years that have passed. Okay, so really quickly before we move on, I want to look at a couple of things. Things you might notice is in each case we have our starting value times our multiplicative rate of change to the T, and then here we had our starting value times our multiplicative rate of change to the T. So in each one of these scenarios, we're going to generalize. We're going to say, in general, we can say that if t begins at 0, okay, then our initial value times our multiplicative, that means like the multiplier, multiplicative rate of change raised to, I'm going to put right here, t begins at 0, which is important because we're going to talk at different ones that begin with t equals 1, and it's a different scenario. So if t begins at 0, and we start building this change, we're going to say that our output is our initial value times our multiplicative rate of change raised to the t. Okay. So you can sort of use this as a guide for what we're going to be doing in class tomorrow. So we're going to start thinking about exponential functions, and then we're going to be using logs to solve them. So this is a good way to think about how am I going to write these functions from context. Okay, I will see you all soon. I hope you are able to watch this video before class tomorrow.